Okay, can you see the PowerPoint presentation screen now?
Yeah.
Yes.
Good. Let's see if I can have the slideshow going on correctly, and you see the audio view, not the presenter view, correctly.
Yeah, we see like full screen slides.
Okay, so it's been a while since we met last time. It was before the winter vacation. Let's recap something we learned from there. We had the topic about metallurgical objects and how the fatigue crack is growing in them, how the process goes, what kind of modes the fatigue crack growth can exhibit, what factors do affect to the crack growth. And we learned something about the Wöhler curve. What is the background of the Wöhler curve? How is it formed? What does it mean? And how has it been used? And also, and I would maybe underline most importantly, we looked at the topics about how to improve a fatigue life of a component generally, even without performing any calculations. And that is really, really important thing for you to understand and comprehend these topics. So there were these three main lines under which there are more detailed actions that can be done. First of all is the increasing of the local strength. Second is the reducing the local stress. Third one is to prevent the harmful ambient effects. And in all these actions which can be done below these, the practical actions, you should remember that the fatigue crack initiation is always a local event. So the local area where the crack wants to be initiating and wants to grow is the area you need to affect. You don't necessarily need to affect large areas. It could be only very small area and you can still gain benefit out of it. Okay, for today we are going a bit deeper into the topic of fatigue in a way that now we learn how to dimension or assess or calculate structures against fatigue. And the approach we are learning today is so-called infinite lifetime assessment method. What that means? It means that when we speak about infinite lifetime, everybody understands that it is theoretically infinite because nothing lasts forever. But theoretically, the component for which the stress variation is below the fatigue limit will last forever. But we must keep in mind that this only applies to steel and titanium and some other materials, but not, for example, to aluminum. But most often we are dealing with the steel structures, so we can base our dimensioning on this. And the idea is that when we have in this y-axis, we have the stress amplitude, meaning the variation of the stress. The variation, sigma A, is below the fatigue limit. Then there is infinite lifetime. And this is by far the most important fatigue assessment method there is. And I would say that 95% of the cases you would need fatigue assessment can be covered by this. This is the basic method that is being derived from Mr. Wöhler's investigations, and from that reason, it has quite some history. So there's quite a lot of good data available, material data for performing this analysis. So for quite a few materials, you can find the fatigue limit values for example, stress ratio R-1 or stress ratio R/0 loadings. But even though if there would be no specific fatigue limit available for some steel material, there are very good estimates available, especially for steel, and they work pretty well. And that is something we are going to learn today. And also we can estimate the sloping part of the Wöhler curve by using these methods by Mr. Juvenal and Shigley. But that is something which is outside of the scope of this course. But in this course, we are dealing on the assessment of the infinite lifetime against fatigue limit. Because when we go into the sloping part of the Wöhler curve, it would mean that we are on the finite lifetime region. So that there would be some specific number of cycles that the component would last. Also, as it's been investigated quite extensively, there are quite well different kind of softwares available for infinite lifetime calculation, and also there is some finite element method that you can use. There are even embedded tools in the finite element softwares that you can use for fatigue assessment. But of course, when using those, you will need to know what are the basics of the fatigue, what are the loadings, what is the function of the Wöhler curve. Otherwise, you don't benefit much out of the result if you don't understand what the machine is doing. So what we need to do when we are performing the analysis for infinite lifetime calculation, it means that we design the component such that when we include all these factors, meaning the fatigue limit reduction factors like mean stress, surface roughness, size effects, other effects, and we include the effects of local stress increasing factors, which are usually the notch effects. When we take all these into account, we still have the stress amplitude below the fatigue limit. It is as simple as that. But what is important to note that we need to include these effects because they have significant effect on the results. And if we don't do this and we just do the plain calculation with normal strength analysis methods and the stresses, we will not get reliable results. So, as mentioned, this infinite lifetime approach is it's suitable for most cases in everyday engineering. It is good for relatively large lifetime requirements because we understand that if we calculate the component against infinite lifetime, the number of cycles that is, for example, from the application is usually quite high. It could be, for example, a rotating machine that is spinning like 1500 RPM per minute, RPM, and therefore the number of cycles is really high. Or if the number of cycles during the lifetime is very low, for example, a crushing machine which is operating very slowly, or some other machine, it might be beneficial to use the infinite lifetime method if we don't need to precisely optimize the use of the material, which means that we can use the infinite lifetime calculation. It provides quite significant additional safety, but who cares? It lasts. And there might be some kilograms of extra material, but if we are not worried about that, we can work on it. Also, it's important to note that there shall be no local yielding due to the notch in the component. If there is local yielding due to the notch, we cannot apply the infinite lifetime method because we are not in the range of this method. Also, same reason, we cannot apply if there is already an initial crack. If we have found that there is in some component, there's also already a fatigue crack that is initiated, then our calculation method doesn't give any reliable results because there is also already the crack propagating, and infinite lifetime method is based on the assumption that we can prevent the initiation. so that initiation will never happen. That is the base idea behind the infinite lifetime. And if there already is the crack initiated, then we are already outside of the game area of the infinite lifetime method.
So I'm a little bit confused with the notch effect. So in one of the first slides, you say that we should take into account the notch effect because it's stress amplitude increasing factor, right?
Mm-hmm.
But here you say like we can't apply the infinite lifetime because of the notch effect.
That's a good point. It might be here. I could rephrase it maybe. This means that if we have, even though we would have a nominal stress below yield point, but then we have some notch that will sort of increase the stress in that location above the yield limit, it means that we cannot apply the infinite lifetime method.
So we just need to check whether it works or not.
Yes, exactly. Exactly.
Okay, great.
Exactly. That is important. So if you know that you have a journal or notch, and you have to first calculate what is the stress, including the fatigue notch factor. You have to use the fatigue notch factor, and if the fatigue notch factor is such high that it will increase the stress level above the yield limit, then you are not able to apply this method anymore. That was an important topic and very good question.
So we just use common sense, basically.
Yes, basically, yeah.
Okay.
And also, it's not applicable because it cannot predict the crack growth. It cannot be used for precise assessment of crack growth period. If you want to utilize the lifetime which is remaining after the initial crack, then of course you would need to use fracture mechanics. This doesn't apply. That is also common sense. So therefore, in those cases, you will need to use finite lifetime methods. And this is basically the rest of the slide is something that we cover that topic, but we don't go too deeply into those methods, how to use it. So if our local stress amplitude exceeds the fatigue limit, meaning that in this picture here, this purple sigma A would be somewhere over here. It would mean that we are above the fatigue limit, and then we would hit the Wöhler curve sloping part, and then that would give us a finite lifetime. So therefore, if we already know that this local stress amplitude, including the notch factor, will exceed the fatigue limit, then we are out of the scope of infinite lifetime method, and then we have to use this finite lifetime methods. And usually for these applications, the lifetime requirement is smaller, of course, because it will give us smaller lifetimes. But then it might be that we need to optimize the structure. We are not able to build the components that thick that we would keep the stresses below the fatigue limit. Therefore, we had to make them more slim. And then we are already in the region of the finite lifetime. Or if we need to include the crack growth, then of course we need to go for the fracture mechanics. Or if we have a welded constructions, because there are always residual stresses and there are discontinuity effects that will reduce the fatigue life. So for welded component, basically, you could say that you never achieve infinite lifetime due to these reasons. It might be very long though, but it's safe to assume that there is no infinite lifetime for welded constructions. Okay, so here we checked these two main things, what we need to include: fatigue limit reduction factors and stress amplitude increasing factors. And now first we are going on to the fatigue limit reduction factors. What are those and how we can define them? So from the book of Norman E. Dowling's Mechanical Behavior of Materials, we find this division of fatigue limit reduction factors. First of them is size factor, second one is surface factor, and third one is other factors included. There could be temperature, corrosion, wear, radiation, whatever. And when combining these, we get the overall combined reduction factor M. And of course, all these factors, they are in value, they are smaller than 1. So they will reduce the fatigue limit. First of all, there is the component size effects. There is freezing sound. It's freezing cold here.
I had some problems while you were reading through the slides with factors, but then it came back to life.
If you encounter the same, that you miss some of my sentences, please note that's a good way to do it, because at this time, sometimes the Zoom is giving me information that the internet is unstable, and then I might know that you might not hear, but now I didn't see any note about that. So, okay, so the size effects, and this ranges back to the history of August Wöhler, who already found that when we increase the physical size of a component, only that will reduce the fatigue strength, of course, within the same stress level. If we have a small component with 100 megapascal of amplitude and a large component with the same stress level, the large component will have a shorter fatigue life. This is basically the same for static strength. In tables for different thicknesses of steel, you might sometimes find different values of yield strength for more thicker plates. And the idea behind is that usually in the thicker plate, it is not that easy to perform the crystal grain structure within the material as consistent as it would be in a small component. And therefore, usually the grain size, especially inside the material, is larger, and larger grain size usually means lesser strength. And this has especially effect in the fatigue if we have the maximum stress amplitude somewhere inside the material. That is not very common, but in some cases that might be the case as well. Usually the maximum stresses are at the surface, but maybe in some cases they could be inside the material. An example of this kind of case is, for example, a rolling contact in a bearing, where this maximum stress might not be exactly at the top of the contact surface, but a little below in the material. And also in a large component, there is the probabilistic idea is that it is probable that in a large component there are more inconsistencies in it. There could be inclusions or some other non-ferrous or non-steel materials inside a bigger component than in a small component, just out of pure probability. And therefore that will provide the sort of stress increase in place for a notch to for the crack to grow. So therefore we need to include the effect of component size. Here we have some kind of table for steels, and you can note that there is somewhere in this diameter, in the x-axis you find the diameter. If we go smaller, we can actually gain out of the size. So if the component is small enough, we can increase the fatigue strength with this factor. And in this table, it's stated that the sort of the 0 point or the 1.0 factor would be at 7.62 millimeters. I don't know if it's by accident or something, but it is actually the same as the rifle bore for some reason. But nevertheless, if the shaft is bigger than that, it will reduce. And this table is for smooth rotating bending. So for that kind of load only. But also in the Dowling's book, there's another table which is not that specific. There we find bending or torsion, and there is a variation from less than 10 millimeters up to 150 millimeters, and this is not very specific. And unfortunately, this is only up to 150 millimeters in diameter, so it means that it's not applicable in all cases. But similar factors can be found in multiple of sources. You can also Google them by yourself. One more that I'm showing here is a size factor equation, which is proposed by Niemann und Winter's Maschinenelemente, which is excellent book. If you know how to read German, I can recommend that to you. And here you can find an equation form how to calculate the size factor. There are some factors AD and DF and DREF, which you will find when you check these tables in the next page. So it depends on the material and it depends on the shape of the component. This is more detailed and maybe more academic way of approaching the size factor. And I would advise you to use this when you are doing the project work. It is not. It's the best to use this one. It's okay to use the tables as well, but this is more, I would say, more academic way of approaching it.
Sorry.
Yeah.
I missed the box. So can you tell me why the factors have to be smaller and equal to 1?
Because they are reduction factors. Because usually the idea of this factor is that they will reduce the fatigue strength. So therefore they had to be smaller than 1 because it's been multiplied. The fatigue limit is been multiplied by these factors, and then the factor of course needs to be smaller than 1.
Okay.
But as we can see here, for certain sizes it can be actually increasing factor, but usually it's reduction. Most cases. Then we have the surface finish effects. So if we have a very rough surface, that also has accelerating effect on the crack formation. You could consider very rough surface as a small micro local notch, and that will ease the initiation of the crack. Here is one table for surface finish effects, which doesn't include the RA surface roughness values, but it's just more general considering the manufacturing method, how the components be manufactured. There are others also which include the actual RA or RZ values in the equations, and you can find them, for example, in this previously mentioned Maschinenelemente, but this table is quite okay to use in the project work. And also it includes somewhat the effect of the ambient conditions, at least if it's in water.
What? Áo dễ ôm à? Bớt. Đây là cái để bụng anh đủ mà anh nói á. Mẹ đây giờ.
Mic on.
Lặng đọc bài.
Okay.
What was the unit for ultimate strength? That was in a previous page. It says KSI.
Yep, that's a good point. This is KSI because it's American table, so that stands for, I think it's kilopons per square inch or something like that. So when you apply this, you will need to find a converter. Web is full of converters where you can convert the KSA value into megapascals and vice versa. In today's task example, I also have denoted I have marked what is the relation between those, so you can use that as well.
Okay, thank you.
Okay, but that's not all. There can be and usually are also other effects. And a good engineer is always able to judge that are there something else that we need to include, because there are multitude of other variables that can affect that, and the effect could be positive or negative. You never know. Like temperature, and that applies to not only static strength but also to fatigue strength, that when you increase the temperature, the strength is lower. Also, if you have some layers in the microstructure, if you have, for example, some kind of stellite coating or very hard coating, hardening in the surface, that will of course have a positive effect. If you have a corrosive atmosphere, it will have a negative effect dramatically. Seawater is one of the most severe ambient conditions that the steel component can be put into, because it's there is corrosion, and when you have simultaneously variable loading, the crack will propagate really fast. Abrasion is something you might need to take into account. That is also negative effect, and in some very special cases also material aging. Maybe not so much with the steels, also with some steels, but usually with other materials at least. In nuclear power plants, there are places where the radiation is so high that at least certain stainless steel tends to brittle. So the high radiation changes the crystal grain structure over time. And if you have a component like that, then you would need to include that into the analysis. And also good to keep in mind that you would need to assess all of the effects during the total lifespan of the component. So you might need some other strength factors. If you don't know them, then you would need to guess, or then you would need to dimension the component in a way that the residual safety is sufficiently big, which will overcome the uncertainty in the effects. Here's a chart also from this Maschine-Elemente about how the temperature affects to strength of the component. So the steels, general steels, are here shown in the solid green line, and the cast irons here with this dashed line. I think at least Bea might be able to read that book by your own. When you go back to Germany, I think you will find that in the library immediately.
I've already downloaded it.
Really? Is it
Yes.
in PDF?
Yes,
Available?
but from my home institution.
Yeah, of course. Yeah, it's if you buy it, I have it as a book, and it's not that. I would say that it's quite pricey, but it's a good book. Okay, but the effects are not only there, because there are also other effects. And last time we spoke about the mean stress, and what is the meaning of a mean stress. We looked at different stress ratios, and that is something that defines how this stress variation is located. Located in respect to the zero line of the tension. So the mean stresses can vary. So the mean stress can be to some point, the mean stress could be at the zero when the loading is tension plus compression, or it could be something in between. And this mean stress, it has significant effect on the fatigue life. Everybody understands that if we have a component where we increase the mean stress while we are still keeping the same stress variation, of course the lifetime would be shorter. The problem is that usually the tensile test material data is available for certain stress ratio, normally R-1 or R0. These are the stress ratios that usually test data is done. But in our practical cases, the mean stresses are usually something else, like here. And it doesn't match to R-1 and R0 immediately or directly. So therefore, we had to include the effect of different mean stress levels, and there are number of proposals how to do that. There are Goodman equations, Smith diagram, Gerber parabola, Haig, Söderberg, Gomez, Jaspers, and others. But basic idea behind all of these is the same. So basically, all of them follow the same principle, and the idea is that they will modify the stress amplitude such that it will include the effect of the mean stress. So for example, comparing to this R0 situation, considering that we would have the test results with R0, if our mean stress is somewhere up here, we would just increase the amplitude of the variation and still use the same test data. That is the basic principle. And how we do that, here is the equation of the Goodman. That is something we are going to use in this course and also in your project work. If you are interested in, you can find these others in the literature. And the equation is quite simple. So in the equation, we have this term for fatigue limit for any mean stress. And that is something we want to calculate. This is something that we want to know. What is fatigue limit for our mean stress in our case? Then we have, there's an error, there should be AR. I had to fix this. This ER or AR, it's the fatigue limit for the known mean stress, usually R201. And this is something we can get from the test data. Then we have the mean stress, which we can calculate from the loads. And then we have the ultimate strength, which we also get from the material test data. And now when we solve this equation so that we can obtain the sigma E, the value that we want to know, we can form this equation into this kind of shape. But now, initially we had a question about how we can know what is the material fatigue limit for zero mean stress. For certain materials, we can find the data, but there are numerous materials for which we might not get the data. And then we can use this approximation, because for steels, this approximation works quite well. This fatigue limit for a smooth unnotched component is 50% of the ultimate strength of the material. And this is basically ingenious because it's working quite well for, I would say, most of the steels. Only very high strength steels are outside of it. But most steels are working quite accurately with this equation. So the fatigue limit for unnotched, if we don't include the notch effects, unnotched component is 50% of the ultimate strength of the material. And when we combine this information with the equation here, we will find this equation number 8, which will give us the fatigue limit for any mean stress level. Sigma E is the fatigue limit, and for any mean stress and with any material ultimate strength. Ingenious, I would say. But something that you need to consider is that, okay, it's applicable only to the milder steels, not super high strength steels, only up to 1400 megapascals, which is in most cases quite enough. But also you need to include the notch effects, meaning fatigue notch factor in the calculation of mean stress sigma. You had to be including those while calculating the mean stress. And then we have found what is here, what is the fatigue limit that we can use in the calculation for a material for which we otherwise wouldn't know what is the fatigue limit. And now this applies to the method that we are today performing, the infinite lifetime. But if we would have a component for which we want to know what is the finite lifetime, and we need to assess this fatigue limit for certain material for that, there are also methods for that. We don't go too deeply into it. But if you never need ever need to do the calculation for this sloping part of the Wöhler curve, the finite lifetime region over here, then you can, for example, check this method of Mr. Juvenal or Shigli, presented at least in this Norman E. Dowling's Mechanical Behavior of Materials, probably in somewhere else as well. But that is something that good to know for you. We don't need that in this course. And now, when we have calculated all these modification factors, we have calculated the sigma E, which includes now the mean stress, and we have calculated the fatigue strength reduction factors. We can calculate, for our case, the modified fatigue limit. And this is now the fatigue limit we can use in the calculation against the loads. So this is basically our strength in this assessment. Okay. Then the stress amplitude increasing factors. So now we covered, in here we covered these fatigue limit reduction factors. And now we are going into the second topic, stress amplitude increasing factors, which we also need to include. And that is something that you already know. That is something we've been practicing. So that is basically the notch effect. This is already known to you. So from a previous lecture, you know how to calculate the notch sensitivity using these equations and using the tables or using the online calculator for elastic notch factor. And if we use von Mises stress, we can apply the equation of the von Mises. In today's example, we don't need the von Mises because there's not a case of combination of stresses. But if there would be combination of different stresses, we would use von Mises as well. And now, when we have done this calculation, we can just simply calculate the safety factor as if we were doing for static strength calculation. So here, sigma EF is the fatigue limit that we have now defined using the strength reduction factors and mean stresses. And the sigma A is the loading. That is something that we obtain from the structure using normal strength approaches. But you had to include, of course, the fatigue notch factor in this sigma A. Otherwise it's not in the range. Okay. And the calculation task for today is to calculate this kind of component. So there's a small shaft of steel. And now the case being that we don't know what is the exact material grade. Therefore, we don't know what is the fatigue strength exactly. But let us assume that we have done a test, taken a test piece from the bar and done a tensile test for it, and we know that the ultimate strength is 800 megapascals for this material. Also, we know that this environment is non-corrosive. There's room temperature. Dimensions are smaller diameter 32, bigger diameter 35. and the radius in between 1.5 millimeters. The loading is bending loading fully reversed, which means that it's R-1. So the same bending stress is fluctuating between plus and minus. Same amount of tension, same amount of compression in the tension, in the bending. And the amplitude is 350 newton meters. And in addition to that, there is a constant tension load, F, which is 25 kilonewtons. That will now provide you the mean stress. And now your task is to define the safety factor against infinite lifetime. And here is the conversion factor from megapascals to KSI, which you will need in defining one of the M factors. Okay, so you can start, and I will be here to guide you if you need any help.
Okay, was this all theory for today?
Yes, this is all of the theory for today, and this same lecture material is available in the Moodle.
Okay.
So Tirkkonen, do you have some other things to do at the moment?
Yes, like a lunch. But so see you next week. Bye.
Bye.
Yeah, I'm gonna also head out to lunch since there will be no new topics for the day. Thanks for the lecture. Bye.
Tom, do we include size factor for those calculations?
Yes, you will need to do that.
Okay, thank you. So we just use the table, right? Or we calculate it?
You can use the table, but it might be that you will get different results from me. Let's see how I think I used the equation. Yes, I did use the equation for defining that. So if you want to compare your results with mine, then I suggest that you use the equation.
Okay, I'll calculate it then. Okay, thank you.
Tuomo, I wanted to ask about the project work.
Yes.
Because I don't know if we have to start right now or not, maybe in some weeks, or how it works.
I haven't been assigning you the task yet because you haven't had the knowledge to perform it. Today's lecture is one of the key things in doing the project work, and I didn't want that anybody makes any unnecessary work. So within next week, I will assign you the project works, and because by now you have gained pretty much the knowledge that you will need to perform the work.
Okay. Okay, thank you. To find the notch factor, we have to use this link, right? Or we have to use a table.
Okay, I was muted. You can use the tables, but I would prefer you to use the link.
Because I don't know why, but the link is not working to me.
Okay. There are some things that affect. It doesn't work always. It seems that the site is down every now and then, at least for me. Let's see if I can access to it.
Well, I can add that there is a problem with link. I don't know, even if you use it, and then copy same link, it doesn't work. But you can just click this just concentration to the left when you reach the site, and I think it's the easiest way.
Here's the stress concentration. Yes, I do it always. I go from the Google. I just write into Google e-fatigue, and then I come to this page, and then I click stress concentration.
Okay.
And then here you have the rounds and shafts. Click onto the arrow, and then you can select from here round shaft with a single fillet. Sorry, I did it incorrectly. It's here is the trick that I think it was at least some point that you need to click onto the text here. So if you click, let's go back. So if you click here at this location of the picture,
Yes.
it will lead you nowhere. So you had to click onto this blue box with the text inside.
Okay. And I have to fill the gaps with my values, right?
Yes, here you just input the values that's been given in the assignment, and then press calculate, and then you shift. The first page is for tension, then you shift over to bending.
Okay.
Unfortunately, you need to input the same values again, and the same for torsion. So the input values don't copy from this sheet to another.
I am trying to enter and it's not working, the eFatigue link, so I don't know what's the problem.
So does it say something, or what happens to it if you are in the page?
If I try to enter, it puts like the connection is not safety and I cannot I cannot continue. I don't know why.
Okay. Well, yeah, then it might be with your computer. Then you need to take the values from the tables.
Oh,
What browser are you using? Because you can anyway visit the website even though it's unsecured connection. If you click the button like more information or anything like this, it should be to the left, and then you can select like proceed to website or anything like this. Try it.
okay, that's right. That's right. Thank you. Right now I can enter.
Yeah, I have some issues with both browsers.
Okay, thank you so much. Sorry, Tom, I have another question.
Yeah, please go ahead.
Yes, to calculate the fatigue notch factor, we have to use the formula. So first of all, we find the KT of tension and bending, right? Using
Yes.
this link. But then we need to know the beta and how do you know this this beta?
That is something that you need to check from the table that is given in the lectures, where you can find this notch effects, page 21. And you have this Neuber equation for notch sensitivity, and next to it there's a table or
Yes.
graph where you can read the beta constant.
Okay, so I have to find my ultimate strength
Yes,
and then find the beta.
yes.
Okay.
Isn't ultimate stress is given in the in the task already?
Yeah, that was given in the assignment.
So I'm now calculating factors. So I wonder, do we need to take into account surface finish factor for this problem?
Yes, you would. So in the task assignment, it was stated something about the thing. It's been machined shaft of steel, and also there is some other information about the environment. So with that, you should be able to find
Okay, but yeah, continue.
Yeah, and also you need to take into account that this x-axis for the surface finish effect, it's in KSI. So you need to use the conversion factor I gave in the task assignment, or alternatively, you can use a converter you can find on Google. If you, for example, Google MPA, KSI to MPA, you can find a converter for that.
So we can just look for a table, right? So we are not given any extra information in the task itself. I also have a question about size factor. So here, if I want to use Niemann formula, give me a second. So what is AG? I'm a little bit confused. And what are the differences between DF? I suppose it's effective, and DREF.
Yes, those are the ones that you can find in the next slide in these tables. So depending on the material, the equation uses different DREF and different AD. Mm-hmm. And the DF is the efficient diameter, which is for a round shaft as we have now. It's the
one last question, or maybe not last, but regarding the size factor. Yeah, so logarithm, is it like the 10-based logarithm, right?
Yes.
Yeah. Okay, great.
But if you try different values of beta, eventually you will find that depending how do you look on the scaling from this table, it doesn't have that big effect on this value Q and eventually KF. So if you happen to mismatch beta value, maybe 10 or 15%, it really doesn't much effect onto the KF.
So it's correct to say that beta is 0.1, more or less?
Yeah, that's fairly close. I use 0.08, but if you use 0.1 instead, let's see.
Yeah, I know it's so close. That's the reason that I didn't know if you use exact number or not.
Yeah, it has a slight effect. But the effect is in such a direction that if you use smaller beta, you will eventually get larger KF.
So it's better if I use 0.08?
Yeah, I think I've been using 0.08 for that.
But the problem with the table is that sometimes it's difficult to find the correct number.
Yes, especially in that table, because it seems that this interval between 10 to power minus 1 and 10 to power minus 2, it doesn't include all the tick marks. So if you count them, there are not enough of tick marks to cover that.
Yes. Well, thank you.
I will put now some of the results to the Moodle under lecture 8, so you can check your calculations against those. And also in the project work, you can see that depending on how you look onto the tables, you get slightly different values for example, KF and the other reduction factors. So there is some margin in the results that I will approve, of course, that what is reasonable. But if there is like a bigger deviation to the real correct results I've done, then there might be a question about that. It's not correct, but there is some range within where you can consider different values all fairly okay, because it's never that exact when you have to look at the tables and define the parameters from there.
So can we basically say that reduction factor for temperature or environment is going to be approximately 1?
Yeah, that's the
Okay.
case because it's in the room temperature.
Yeah, it's quite close to the one on the graph.
Yeah, it's basically one. The thing that you can see if you look at the graph is that steels tend to lose some of their strength slightly after 100 degrees Celsius. So, but that's this is chart which is could be useful for you as well, not only when defining the strength for fatigue, but also when you do static strength analysis. You would maybe face into some structures where the machine or structure is in elevated temperature, and you could use the same chart for static strength as well.
After we get all the factors, we just multiply them.
Yes.
Okay.
And when you have to find the mg, it refers to the diameter 1 or diameter 2. I know that in this case it doesn't matter, but
it's a diameter 1. It's actually, that's quite a good question. I've used diameter 1. If it's I've never actually considered it that way. I've used the diameter 1 or the smaller one due to the reason that the smaller diameter is the one from where the crack usually starts or where it initiates, because usually in the smaller portion or just in the transition phase where the smaller diameter is changing to a bigger one with a radius, that is where the crack is forming, and therefore that is more important. But
okay.
There might be maybe cases where the bigger diameter would be more appropriate. Yeah, but in this case, use the smaller.
Great, thank you.
Tilma, do we use von Mises for nominal loading stresses?
You don't need to use von Mises, well, it doesn't matter if you use, because the result is the same, because you only have these tensile components in the stresses. If you put them all into the Mises, you will get eventually the same result as without.
Yeah. However, we need to calculate the mean stress.
The mean stress is coming. Now you need to check the loads. So when you see the task assignment, it was given that you have the constant tensile stress. Just a second, I think I will take my drawing table and draw a little bit. It's easier to explain. Okay, can you see my white screen now?
Yeah.
So you have the case, you have this shaft like that. And you have the bending loading, which will cause into here this kind of distribution. It's maybe too little. Let's make it bigger. So this is the distribution from the bending. And now when this is amplitude, it means that it is pulsating in the both sides. So while pulling downwards, it means that we have here tension and here compression, right?
Yeah.
But when it's going upwards, it's vice versa. So that is causing the amplitude. And now when we have this tensile force, that is causing evenly distributed stress distribution over there. And that is now the base level from which the bending amplitude is sort of fluctuating around. So this F is creating you the mean stress.
Yes, I guess I confused the bending moment amplitude with the bending moment itself. So taking into account that we know the R and we also know the amplitude, we can calculate the maximum, well, not maximum, but maximum absolute value of the bending moment.
Yes,
correct?
we also can calculate this maximum value sigma max, which would be then sigma bending plus sigma, if we put it tension like that, or bending, yeah. But we don't need that anywhere because we only need this mean value, and we need the variation from there. We only need the mean value and the amplitude.
Mm-hmm. Yes, I just I don't really understand how do we then sum it up to get the sum total stress or anything.
The reason is that if you put into von Mises the bending normal stress and the tensile stress from tension, you will add them into the von Mises, right?
Yeah, and it's like the total stress.
Yes, because the stresses are similar. So both the tensile stress and both the bending will induce tension into the top surface, and therefore we can just simply add them up. If there would be some other stress components included, if there would be, for example, torque also, then we would need to use von Mises because we cannot just add up torque with the bending stress. It's a different stress component.
Oh, I so dumb. Yeah, because it's bending moments and tensile stress is like they give us normal stress, of course. Yeah.
Yes.
Yeah, and we just
exactly.
sum it. Okay. This is quite stupid.
This is the reason we are doing this. It was a good discussion. I think somebody else also may have gained from it.
Oh, wow. Thank you.
Okay, so I think time is up for today. So I did put actually already the values I got. You might have some differences depending on what kind of values you've been using, but you check them with the input parameters I've been using. And there were some typos in the lecture for today, so I will update that as well and set it in the Moodle. So have a nice rest of the week and stay safe. Don't catch up Corona, and we'll see you next week.
Thank you. Goodbye.
Okay, bye.
Goodbye.
Bye.